Let's go up the layers. Welcome to the link layer, our layer 2, as you see on the right hand side in our reference model. So on top of the physical layer we have the link layer, and the link layer, as we will see, then delivers frames, packets, we call them here frames, on the link layer, layer 2, to the network layer. This is where we have our internet protocol. So why do we need a link layer? What are the tasks of a link layer? Well, the tasks are a major component here of the content of our chapter. So we will talk about framing. Here in this context, this means how do we get a frame out of the bit stream? The physical layer, as we know, delivers a stream of ones and zeros, a bit stream. How do we recognize a frame? Then I also told you that the physical layer does not care about errors. So how do we now detect errors? How do we maybe correct errors? We will talk about flow control, because maybe you're connected with a weak mobile device directly with a supercomputer. Well, so maybe the supercomputer will send too much data. How do we control this flow of data? Then we have to talk about medium access control. This means what happens if several devices want to access a medium, for example, simultaneously. How do we control this? Then I will give you some examples for protocols of layer 2 and talk about the infrastructure. Okay, so link layer provides services to the network layer, as I said, framing, error control, etc. And the link layer uses the bit-by-bit service of our physical layer, and we know that the physical layer will then send signals over a physical medium. We talked about non-return to zero line or cable codes. We talked about modulation. So who does all this? This all integrated in what we call a network interface card. So all the devices, your mobile phone, cell phone, your desktop, PC, switches, we'll see, routers, etc., wireless, wired, they all have a network interface card. So why? Well, this card provides some abstraction inside the network stack. So the card allows us to send and to receive frames. Frames, this term means packet on layer 2. So they're called frames here. The link layer now manages the communication between those network interface cards. You remember, in our layered architecture, the peers talk to each other. So one network interface card then transmit data to another network interface card. Typically, you have at least one of these, but there are also devices with several network interface cards, like, for example, your smartphone has several. Think of wireless LAN, Wi-Fi, cellular network, and then at least we can receive satellite signals, send and receive Bluetooth, near-field communication, and so on. So we have several of them. Okay, so typically layer 2 and layer 1, they run directly on this network interface card or with the help of drivers then running on a CPU. But there are also complete hardware solutions, because at the end of the chapter you will learn, okay, there are network interface cards that are capable of handling 400 gigabit per second. You cannot do this in software anymore. So what types of network interface cards do we have? There are two types, two classes. One is what we call a point-to-point NIC. So that's the typical setting. You have a fiber between, let's say, Europe and the US, and there is a fiber in between. Okay, connecting this, then typically you have one NIC on the European side and one then on the US side. Or you have your PC on the desktop, and it's connected then to your switch somewhere on your floor. So that's a point-to-point NIC, and this is used for really high data rate links, and what we'll learn that this is a quite simple situation because there are no what we call collisions. What is a collision? Well, if several elements try to use this resource, then it could happen that we have collisions. In this simple case with a point-to-point NIC, there's only one sender and one receiver, or the other side is the sender, and we have here on the left-hand side the receiver. So if it's a full duplex transmission system, then there are no collisions at all. So it's very simple, very straightforward, as we will see. But there are also situations where we have something that's called a broadcast NIC. So all the wireless systems, they typically broadcast. So Wi-Fi systems, you have your Wi-Fi hotspot sending something to the devices, but also the devices can send something to the hotspot. But all the devices will then also receive the transmissions. So this is a broadcast system, and the network interface card has to be able to handle the problems that may occur here. And the major problem here is we can have collisions. So what happens in this setting if now here in this example, two devices want to send something at the same time, same frequency? So you have this device sending something on a wireless LAN, and the other device sending something on a wireless LAN. Then you will have a collision. And we have to be able to handle this. I will go into more details here in the course Mobile Communications, but this is a principal problem, so broadcasting. So it's a bit more complex, and this is exactly where we need those medium access control mechanisms, so MAC. We also have to talk about addressing. Why? Well, in this broadcast situation, what happens if your Wi-Fi hotspot sends something into space, a message? Who is the receiver? It's very simple up here in our point-to-point scenario, because, I mean, if the right-hand side sends something, the receiver on the left-hand side is clearly the receiver. There is only one receiver. So it's very simple, and vice versa. But in the broadcast case, well, who is the receiver? So we need addresses. Okay, so there are some differences, and we'll talk about this during this chapter. Okay, first task. Quite important, framing. Why do we need something that's called framing? Well, remember, the physical layer delivers simply ones and zeros. That's all, including errors, but we'll handle errors in a second. So, how do you know that a frame now starts? So is this the start of a new frame here? And maybe before that we had, I don't know, noise or whatever. So we have to organize our messages. And that's exactly the idea of framing. So is it noise? Is it data? Where does it start? We have to organize this bit stream. So you receive something from the physical layers. This is just ones and zeros. There's nothing in between. And we have to say, okay, here frame 1 starts. So somehow we have to notice that this is the start of a frame. And this could be, for example, a special pattern, 10101101, whatever. So a special pattern of bits indicating this is the start of a frame. I will come back to the problems with having such a pattern. But for now, maybe we say, okay, we have this special pattern and we repeat this special pattern 4 times, something like this. And then this means now a new frame starts. Okay? So this is a special pattern, and if we have a special pattern, then we may say, okay, a frame starts, but then we also need a special pattern here that tells us a frame ends. Or we say, as soon as a new frame starts, then this basically also means the old one has ended somehow. So in the end, now this link layer starts organizing, giving some structure to our bit stream. And typically we talk about a header. So layer 2 has to provide a header and typically also a trailer. And then we have something that's called the payload. That is the data you want to transmit. For example, in layer 2, this typically would be our IP packet from layer 3. That's in here. Okay, so a header, and the header then contains certain control information. So maybe we want to say, okay, this is frame number 17. Or, because we have this broadcast situation, we want to say this packet now has a certain destination. This is for receiver number 47, something like this. So this is typical information for the header, so that all the receivers receiving the packets know, this is for station 47. I'm 13, so that's not for me. I don't have to read further. The trailer is typically used for error detection, and with the help of that, maybe also for correction of the errors. But this is for checking, was there an error? And we will learn how we do this. So sometimes this trailer is also called frame check sequence, FCS or CRC, checksumming, etc. And sometimes we also have a special pattern here before we come to the header. Then this is called a preamble. So sometimes we have a special sequence of bits. So for example, our 4 times this 101 whatever, indicating now something new starts. Because as we'll learn, we have systems where there's nothing going on the cable, and then suddenly we have a certain pattern. And this tells the receiver, now take care of the incoming, whatever there's signals. So now there might be a header for you. So this indicates a preamble, typically the beginning of a frame. And sometimes we also have a postamble, so a certain sequence that tells us now this is the end of a frame. So we have special flags indicating the start and the end. Then we have the header giving us control information. We have a trailer typically giving us a checksum for error detection. And then we have the real payload. And you see already here with this simple example that if we talk about certain data rates, bits per second on the physical layer, we lose some of the data rate when we go up in our layers. So on layer 3, definitely we will not have the same data rate we offer at physical layer, because we lose something when we transmit a header, a trailer, a preamble, a postamble, because this does not contribute to our user data. So the usable data rate, the data rate really what we have for our user data, is lower than what we have on our physical medium. Okay, so now how do we do this? So yes, we have to structure our bit stream, but how? And there's a very simple scheme. And this very simple scheme is called character counting, or you can also call it byte counting. So then, okay, 1 byte is 1 character. So why not simply saying, okay, there might be some preamble somewhere, but then as soon as we transmit something, we have a special field here telling us how many bytes or characters do we have in a frame. So the 5 now indicates that altogether we have 5 characters. And the next one, again 5, we have 5. And then we have 8, and again 8. So that's just an example. So we always have a length field. We specify how long is our packet. Very simple idea. So we count the characters, and so we don't need any postambles. So looks good. what could be the problem? Well, imagine if we have an error in exactly one of these fields. So instead of transmitting a 5, we transmit a 7. Just flipping a single bit. That's it. Think that the representation of a 5 compared to a 7. For example, flipping a single bit means suddenly we have a different length indication, now telling us, wow, this frame is now 7 characters long. The receiver does not know that there's an error in the transmission. So the receiver will assume 7 is correct, perfect, then I count, and now, okay, that's our frame number 2. So we lose the synchronization, because what happens now? Now this is 7, okay, then we have a valid indication, oh, that's a very short packet, only 1. And then the 2 tells us, okay, that's the next frame. And then this 4 is interpreted as this 4. And now the 7 is now the remaining characters. So you see frame 3, frame 4, frame 5, frame 6. We completely lose synchronization. So you see, although this idea seems to be okay, nice, so we simply say, okay, now the frame has this and that many bytes. Oh, we have a problem. So, with flipping a single bit, we lose completely synchronization. And there's no way of getting back to some synchronized setting, because the receiver simply doesn't know the length of the real length of all these frames. So we lose synchronization. So, looks simple, but has some problems. Because remember, we may get a bit stream including errors. So the physical layer in this simple setting will not tell us when a frame starts and when a frame ends. We'll see there are also schemes where the physical layer tells us something about the frame, but in this very simple setting, no way. So, counting characters looks nice, but has a drawback. What else can we do? Let's have a special flag telling the receiver, hey, this is the start. That sounds like a good idea. So why not having a special byte, special character, something like this? Okay, this is our flag. Okay, so let's say maybe this flag is now 011111110. So 8 bits, this is our flag. Okay, then I read the incoming bit stream until I read the flag, and the flag byte then tells me, okay, fine, great, this is now the start. Okay, and I could also say, okay, why not having also this flag at the end? Then the flag tells me this is the end. So I've got a special byte in the beginning, a special byte at the end. Again, sounds like a good idea. But what happens if, wherever I transmit a nice JPEG picture of a blue sky, and wherever the coding is in a way that somewhere in between here, suddenly we have exactly this bit pattern? Oops. So what happens if this flag occurs in the payload? That's a problem. Because we do not know what we transmit. I mean, we cannot simply say, okay, this will never happen. I mean, we don't know. This is arbitrary payload. This is an IP packet, and the IP packet may contain some TCP packet that contains some whatever, part of a web page. And so it could happen that the flag shows up in the payload. And the receiver will then say, okay, I see the flag. This is end of the packet. Okay. And then continues, oh, this is some errors data, whatever. Great, here's a flag. So this is again the begin of the next packet. And you see, again, we're out of sync. So it could be the case we have the flag in our payload. So what do we do? Well, there is a solution that's known as byte stuffing or character stuffing. So if we assume we need a byte for characters, so byte stuffing, character stuffing. And the idea is, okay, we use a special character, a so-called escape byte, and this is inserted in the following way. Does this help? So what happens if the escape symbol appears in the payload? We see in a second. So what do we do? The trick is as follows. We always check the original data shown here on the left-hand side. We check, and now this only concerns the payload. If we check the payload and then suddenly we read here, oops, there is the flag. Then we stuff it in the following way. We first insert escape and then we have the flag. Does this help? Well, we'll see in a second. So we do not do this in the beginning. Here it's only the flag. And also at the end, it's only the flag. There's not the escape character. So the receiver learns here, as soon as we have a flag with an escape, then this is definitely not the end in this setting. Because the receiver knows, yeah, okay, I read a flag, the flag character, but now as we have an escape before we have the flag character, then this means, okay, the semantics here of this flag is not a flag. It just looks like a flag, but it's not a real flag telling the receiver this is the end. So this is the very basic principle, and this is called our character stuffing. So only for the payload, we check the payload. As soon as we see a flag in the payload, we stuff it. We place an escape before we have the flag character. Okay, problem solved. Well, let's see if this really works. So what happens if the escape characters itself shows up in the payload? Because this could happen. I mean, escape character is also only a certain bit pattern, so it could show up in the payload field. Well then, the rule is quite strict. It simply says, okay, so we stuff it. So escape, escape. What does this tell the receiver? The receiver has a very, very simple rule. As soon as I see an escape character on the receiving side, I will delete it. This leaves the simple flag, then not interpreted as flag. Or if I have escape character, I delete the escape. This leaves the single escape. So it's fine. Here in the first case, we know, well, it looks like a flag, but it's not because it had an escape before we saw the flag. And the second case, so we delete the escape, then we have escape. Well, then it's an escape character, well, a certain bit pattern. Okay, but what happens if we have exactly the combination escape and flag? Well, the rules are very simple. We stuff the escape, as shown here. Number 2, number 1 was our stuffing of the flag. And now in the situation 3, we see the escape. We stuff the escape. Okay, we have 2 escapes now. We see the flag. Okay, we also stuff the flag with an escape. Again, what does the receiver do? Simple rule. Okay, I read the characters, I see an escape, followed by escape, I kick the escape, then I have our original escape. Then, that's so I see this escape character, then again escape, I delete it, I read the flag. I know now, because there was an escape before we had the flag, that this just looks like a flag. It's not really a flag. So problem solved. It's also not the end. What happens if we have two escape characters, for example, in this situation 4? Well, simple rule. First escape, stuffed, results in 2 escapes. Then second escape, stuffed, results in 2 escapes. On the receiving side, simply kick out the first escape, that leaves an escape. Then we kick out the escape, that leaves an escape. Perfect. So we again have our 2 escapes. So now you can play with this and think of many situations. Believe me, this works. So stuffing, if one of these special characters, escape or flag, appears in the payload field, not when it's really a flag. So that's the idea. Okay, this is now character oriented and this is used. We'll come back to a protocol that uses this. There's a more generic solution that is then typically also done in hardware, because here if we talk about bytes, this could also be done in software. But there's also a solution independent on special character sets. So this pretty much looks like ASCII characters. But what happens if you have a complete different character set, etc.? Then there's a generic form, and this is called bit stuffing. So bit stuffing, same basic idea. We will have a special pattern, and this special pattern, 0, 6 times a 1, and then 0 again. This special pattern should not appear in the payload I receive, because then I may misinterpret this as end of frame, for example. But what happens if it appears? Because again, we don't know what the payload is. And then the idea is to use a very, very simple rule. The sender simply goes through the bits, and as soon as the sender sees 1, 2, 3, 4, 5 bits, it inserts a 0. Always. For the payload, not for the start flag. So for the payload, the sender simply checks, and this can be done in hardware pretty fast. 1, 2, 3, 4, 5 ones, then I insert a 0. The receiver again counts, again also the bits, and as soon as the receiver sees 5 times a 1, it removes the following 0. If after 5 times a 1 there again is a 1, then this will tell the receiver, hey, this is now a special bit pattern. Because the receiver knows the rule, the sender always inserts a 0 after 5 ones for the payload. But as you see, the special flag has 6 times a 1. So, example, if you have original data, we can now simply count. 1, 2, okay, that's not the situation. 1, 2, 3, 4, 5. Okay, 5. We have to insert a 0 here. 1, 2, 3, 4, 5. Again, 5. Assuming this is the payload. 0 here. 1, 2, 3, 4, 5. Again, a 0 here. So the transmitted data looks like this. So we simply squeeze in a 1 after 5 ones, a 0. So these are the stuffed bits. And this is why it's called bit stuffing. Well, be aware, for software solutions, this is not that ideal, because there you have to play with single bits, and the CPUs, they don't like this. Can be done, but this is a scheme that fits perfect to hardware. So what does the receiver do? The receiver, again, now this is true for the payload, The receiver simply checks, okay, 1, 2, okay. This 0, we take this. 1, 2, 3, 4, 5. After 5 ones, I have to delete the 0. If there's a 0, I have to delete it. Again, 1, 2, 3, 4, 5. If there's a 0, I have to delete it. 1, 2, 3, 4, 5. There's a 0. I have to delete it. And this results in the original bit stream. I know that typically you may come up with, aren't there special situations? So, for example, what happens if I do not have the 6 bits like in this example, but maybe a bit stream like this? I have only 5 bits and then a 0 and then whatever will come. So then it wouldn't be necessary to stuff anything. No, you always stuff. So 1, 2, 3, 4, 5. We have to stuff a 0, although this does not look like the special pattern. So we have to transmit 0, 1, 0, 1, 2, 3, 4, 5, squeeze in a 0, 0, 1, 0, 1, 1. Because the receiver will simply go through this bit by bit, 1, 2, 3, 4, 5, then sees a 0 and will delete it. And we are back to the original bit stream. So bit stuffing has a very, very strict rule. We always, for the payload, insert after 5 ones a 0 bit. So that's the idea. But there's also a consequence. Depending on the data, you have to stuff more or less bits. In the previous examples, more or less characters. So it could be the case, think of sending only once all the time. This means we really increase the number of bits. And now the problem is that using bit stuffing, our data rate fluctuates. Why? Assume we have a certain maximum data rate in the physical layer, let's say 1 megabit per second. Now, depending on the bits we transmit, we can use more or less of this 1 megabit per second, because if we send many, many ones, we have to stuff more zeros. If we don't do so, then we do not stuff. Then we can maybe use the full 1 megabit per second. So that lets the data rate fluctuate. And this is something that's not always a good thing. If we use the frame, this counting method, we always have 1 byte, for example, that gives us the number of bytes. And so we have a fixed overhead. Here we have a variable overhead depending on the content of the payload. And this is something that's not always nice. What else can we do to indicate the start or end of frames? Well, the physical layer can help a bit. Yes, we violate layering. Absolutely. Because I told you, no, physical layer does its job. It's a black box for layer 2. They do not really interact besides exchanging data. But yeah, okay, if we violate a bit, we can do something. How? Think back, I talked about 4B, 5B codes or 8B, 10B or whatever. So this means we map our data, 4 bits in this example, here our data, to code words with 5 bits. That gives us some freedom. So for this DC freeness and for coding, we said, okay, no matter how we combine, we never have more than 3 zeros. But as we map 4 bits to 5 bits, we have suddenly 16 code words we can use for something. In the table in the last chapter, we already saw, okay, there are some special symbols like idle, start, quiet, reset. So bit patterns we do not use for user data. We also learned we have 80% efficiency, etc. And now what is the trick? We use now combinations of these otherwise unused symbols for telling, oh, this is the start of a frame. This is the end of a frame. So for example, if we combine JK, this means 1, 1, 0, 0, 0, and K is 1, 0, 0, 0, 1, then this is a start delimiter. And this pattern can never appear in the user data because we saw, okay, for user data here on the left-hand side, we have this set of 16 code words. And they're different from these additional code words we can use for the start or for end delimiter. And you see that this scheme is quite common for certain types of Ethernet. I will come back to this. Also USB interfaces, they use this. So the control characters, they can never appear symbols representing user data. So this is one trick if we violate a bit this strict layering. So with the help of the physical layer, layer 2 can decide, this is start, this is the end. And we do not need then the stuffing or counting bytes. We can also do something else. For example, we can violate code. What does it mean? Well, we know that for Manchester code, we always have a rising or falling edge at the middle of a bit. So you see here this example, we code the 1 here in this falling edge and the 0 in this rising edge, for example. So that's quite clear, and we learned that, okay, this works, okay, the efficiency is not that good, but this is how we can transmit our zeros and ones. And now we can violate this rule that we always have this transition at the middle of a bit. And we can violate it in a way that we say, okay, 2 times this violation, then we transmit a bit indicating the start, then 2 times a violation, and then 3 zeros. And as we violate our coding rules, the receiver will then see, okay, now this is something special, because usually the sender knows how to do this Manchester encoding, but here we violate the code. This tells the receiver something special happens. It's always a question, how can we tell something, oh, now there's something special going on? Well, the problem still is, this must never happen in the user data. But as you see here from the example, as the user data, you always follow this strict rule of, okay, 1 is a falling edge, 0 is a rising edge, and this means, okay, it's absolutely clear for the receiver when we have this user data and what it means. But start and end, they have then special coding violations. Here again, 2 times violating, and now the 0 indicates this is the end, 2 times violations and 3 zeros. So and this shows you yet another example of how we violate the layering. So layer 1 now helps layer 2 on this task of framing. So coming to some simple questions. So why do we need this framing? So why can't we just see, okay, this is now the user data. So why do we need this? And what can the physical layer give us for this? What happens if the physical layer doesn't give us anything? And what is the problem if we have these indications from the physical layer? So maybe we need some more general solution. So we see bit stuffing is a very good general solution, but it also has some disadvantages. What kind of disadvantages? So what could we use without these disadvantages, and what is the general problem if we use these technologies now, for example, from the physical layer helping the link layer? You can do this, but there are certain drawbacks.